July 23, 1944. Aberdeen Proving Ground, Maryland. Captain John Mitchell watched as his engineering team prepared to remove the transmission from a captured German Panther tank that had been shipped from the Normandy battlefields just weeks earlier. The massive 45-ton vehicle sat motionless in the testing facility, its thick frontal armor scarred by Allied anti-tank rounds that had failed to penetrate. But Mitchell suspected that the tank's greatest enemy wasn't American firepower. It was German engineering. What his team discovered when they opened the Panther's hull would shock Allied intelligence officers and provide crucial insights into why Germany's most advanced tank was failing on battlefields across Europe. Hidden beneath the Panther's impressive exterior lay a catastrophic design flaw that was killing German tank crews faster than Allied weapons could destroy them. The transmission that Allied engineers extracted that day told a story of rushed development, compromised engineering, and the deadly consequences of prioritizing production speed over crew survival. This discovery would revolutionize Allied understanding of German tank development and reveal how engineering shortcuts were undermining the Wehrmacht's armored capabilities. The Panther tank, designed to be Germany's answer to Soviet T-34 tanks and American Shermans, was destroying itself through mechanical failures that turned every mission into a potential death trap for its five-man crew. But the story of how Allied engineers uncovered Germany's most dangerous design secret doesn't begin with captured tanks in American testing facilities. It begins with desperate German engineers racing against time to develop weapons that could stop the Allied advance, and the fatal compromises they made when production schedules became more important than engineering integrity. To understand why the Panther's transmission became a death sentence for German tank crews, you must first understand the pressure German designers faced and the impossible demands placed on their most critical weapons program. In January 1943, when German forces were retreating across the Eastern Front after their devastating defeat at Stalingrad, tank development became Nazi Germany's highest military priority. Soviet T-34 tanks had proven superior to existing German armor in almost every category that mattered. American Lend-Lease equipment was flooding into the Soviet Union faster than German forces could destroy it. Most critically, Allied bombing was disrupting German industrial production, while enemy tank output increased dramatically. The Panzer development program faced impossible demands from military commanders who wanted tanks that could stop Soviet offensives while remaining simple enough for mass production in bomb-damaged factories. Engineers needed to design armor thick enough to resist enemy anti-tank guns while keeping weight low enough for existing bridges and transport systems. Most critically, they had to solve complex mechanical problems with limited time for testing and development. German tank doctrine emphasized mobility and firepower over armor protection, but the realities of combat on the Eastern Front had changed the requirements dramatically. Soviet anti-tank guns could penetrate existing German armor at ranges that made traditional blitzkrieg tactics suicidal. Tank crews were reporting that their vehicles offered inadequate protection against increasingly sophisticated enemy weapons. The Panther development program began with ambitious goals that reflected German confidence in their engineering capabilities. The new tank would mount a 75mm gun capable of destroying any Allied tank at maximum range. Frontal armor would be thick enough to resist Soviet 85mm guns. Most importantly, the vehicle would be reliable enough for extended campaigns in harsh environmental conditions. Heinrich Ernst Kniepkamp was born September 15, 1895, in Delitzsch, Prussia. The son of a mechanical engineer who had designed industrial machinery throughout the German Empire, Kniepkamp grew up surrounded by technical drawings, precision tools, and the methodical approach to problem-solving that characterized German engineering culture. His childhood was spent learning to understand mechanical systems and appreciate the importance of precision in complex machinery. Kniepkamp's fascination with automotive technology began during his apprenticeship at Daimler Motorengesellschaft, where he worked on some of Germany's first military vehicles during World War I. The experience taught him that military equipment required different design priorities than civilian machinery. Durability and ease of maintenance were more important than performance optimization or manufacturing cost reduction. After the war, Kneepkamp continued his engineering education while working for various automotive manufacturers throughout Germany. He specialized in transmission design and became one of Europe's leading experts on power transmission systems for heavy vehicles. His work caught the attention of military procurement officers who were secretly developing new weapons despite Treaty of Versailles restrictions. In 1937, Kneepkamp joined the German Army's weapon development program as chief engineer for tank transmission systems. His assignment was to design powertrains that could handle the massive torque requirements of increasingly heavy armored vehicles. The work was challenging because existing automotive transmissions were inadequate for tanks weighing over 30 tons. Kneepkamp's early transmission designs were masterpieces of mechanical engineering that incorporated innovative solutions to complex technical problems. His systems used planetary gear arrangements that provided smooth power delivery across wide speed ranges. Advanced hydraulic controls allowed drivers to shift gears without interrupting power flow to the tracks. Most importantly, his transmissions were designed for easy maintenance under field conditions. But the outbreak of World War II changed everything about German tank development. Peacetime engineering standards that emphasized reliability and longevity became luxuries that Germany could no longer afford. Production schedules compressed from years to months as military commanders demanded immediate solutions to battlefield problems. Quality control procedures that ensured mechanical reliability were abandoned to increase manufacturing speed. The Panther program began in earnest following Germany's encounter with Soviet T-34 tanks during the early months of Operation Barbarossa. German tank crews reported that their existing vehicles were outmatched by Soviet armor that combined superior mobility with adequate firepower and protection. Intelligence assessments suggested that the Soviet Union was producing tanks faster than Germany could destroy them. Military specifications for the new Panther tank reflected the desperation of Germany's strategic situation. The vehicle had to be ready for combat operations by summer 1943, giving engineers less than 18 months to design, test, and begin production of one of the most complex weapon systems ever attempted. Normal development procedures that required years of testing were compressed into a few months of hurried evaluation. Kneepkamp faced impossible engineering challenges that would have been difficult under peacetime conditions and became nearly insurmountable under wartime pressure. The Panther's transmission had to handle the power output of a 700-horsepower Maybach engine, while fitting into a hull space designed for much smaller power plants. Weight restrictions meant that traditional solutions using heavy-duty components were impossible. The transmission design that emerged from these constraints was a compromise that satisfied immediate production requirements while creating long-term reliability problems that would prove catastrophic in combat. Kneepkamp used lightweight materials and simplified gear arrangements that reduced manufacturing time but eliminated the safety margins that ensured reliable operation under stress. The critical flaw lay in the transmission's final drive system, where power from the engine was transferred to the tank's tracks. Traditional designs used robust gear arrangements that could handle shock loads and brief periods of overheating without failure. Kneepkamp's design eliminated redundancy to save weight and manufacturing time, creating a system that worked perfectly under ideal conditions, but failed catastrophically when stressed. The final drive assemblies used thin steel components that were adequate for normal operation, but could not withstand the shock loads generated during combat maneuvering. When tank crews had to make sudden direction changes or rapid acceleration to avoid enemy fire, the transmission components exceeded their design limits and failed without warning. The failure mode was particularly dangerous because it left tanks immobilized in combat zones, where crew evacuation was often impossible. Initial testing of Panther prototypes revealed transmission problems that should have delayed production for additional development work. Test drivers reported frequent mechanical failures that left vehicles stranded during exercises. Engineering analysis showed that the final drive components were failing at rates far higher than acceptable for combat operations. Military observers noted that the transmission problems made the Panther unreliable for extended operations. But production pressures overrode engineering concerns as military commanders demanded immediate deployment of the new tanks. Hitler personally intervened in the development process, ordering that Panthers be ready for the summer offensive at Kursk, regardless of mechanical problems. Engineering teams were instructed to solve transmission issues through field modifications rather than redesigning fundamental components. The first Panther tanks rolled off production lines in January 1943, with transmission systems that engineers knew were inadequate for combat operations. Quality control inspectors documented failure rates that would have been unacceptable for peacetime production, but military necessity required accepting compromised equipment rather than delaying deployment. The decision would prove catastrophic for German tank crews. Operation Citadel, the German offensive at Kursk in July 1943, provided the first large-scale test of Panther tanks under combat conditions. The results were devastating not because of enemy action, but because of mechanical failures that immobilized vehicles before they could engage Allied forces. Over 200 Panthers were assigned to the offensive, but mechanical breakdowns reduced combat effectiveness to levels that made the tanks liabilities rather than assets. Panther crews reported transmission failures that occurred without warning during critical combat situations. Tanks would lose power to their tracks while maneuvering to avoid enemy fire, leaving them immobilized targets for Allied anti-tank guns. Final drive failures were particularly common during rapid acceleration or direction changes, exactly the circumstances when reliable mobility was most essential for crew survival. The transmission failures followed a predictable pattern that engineering analysis would later trace to fundamental design flaws in the final drive system. Initial symptoms included unusual noises and vibrations that indicated components were operating beyond their design limits. Progressive deterioration would continue until catastrophic failure occurred, usually when the tank was maneuvering under combat stress. German field maintenance units attempted to address transmission problems through improvised repairs and component replacements, but the fundamental design flaws made permanent solutions impossible without complete system redesign. Spare parts were often unavailable because production facilities were prioritizing new vehicle assembly over replacement components. Most critically, the specialized tools and expertise required for transmission repair were rarely available in forward combat areas. Tank crews developed unofficial procedures for managing transmission problems that reflected their understanding of the system's limitations. Experienced drivers learned to avoid sudden maneuvers that could trigger final drive failures. Commanders planned operations to minimize the high-stress driving that caused mechanical breakdowns. But these adaptations reduced combat effectiveness and often proved inadequate when enemy action forced crews to exceed their equipment's capabilities. The training manuals distributed to Panther crews contained detailed instructions for identifying early warning signs of transmission problems, but these procedures were often inadequate for preventing catastrophic failures. Drivers were taught to listen for unusual noises and monitor instruments for signs of overheating, but the progression from normal operation to complete failure could occur within minutes during combat stress. The psychological impact on German tank crews was as devastating as the mechanical problems themselves. Crews lost confidence in their equipment and began viewing each mission as potentially suicidal due to the likelihood of mechanical failure in combat zones. Morale declined as experienced crews were lost when disabled tanks became easy targets for Allied forces. Replacement crews arrived with inadequate training on transmission limitations and management procedures. Veteran Panther commanders developed superstitious behaviors around transmission operation that reflected their understanding of the system's fragility. Some crews performed elaborate pre-mission rituals designed to ensure mechanical reliability, while others carried additional tools and spare parts that might enable field repairs. These adaptations demonstrated the crew's lack of confidence in their equipment's basic reliability. The maintenance burden imposed by transmission problems severely impacted German armored units' operational capabilities. Skilled mechanics were constantly occupied with transmission repairs rather than routine maintenance that could prevent other mechanical problems. Spare part shortages meant that many Panthers remained inoperative for weeks, while crews waited for replacement components that might never arrive. Intelligence reports from captured German tank crews revealed the extent of transmission problems and their impact on combat operations. Prisoners consistently reported that mechanical failures were more feared than enemy action because breakdown meant certain death or capture. Tank commanders described desperate situations where perfectly good vehicles became death traps due to transmission failures that occurred at the worst possible moments. The most disturbing testimonies came from survivors of tank crews whose vehicles had suffered transmission failures during combat. These men described the terror of being immobilized while under fire, unable to maneuver or retreat, while enemy forces closed in for the kill. Many reported that they had begun each mission wondering whether their transmission would survive long enough to bring them home alive. Allied forces on the eastern and western fronts began encountering increasing numbers of abandoned Panthers that showed no signs of combat damage. Investigation revealed that most had been abandoned due to transmission failures that left them immobilized. German crews were destroying their own vehicles rather than allowing them to be captured. But the pattern of mechanical failures suggested systematic problems rather than random breakdowns. Captain John Mitchell's team at Aberdeen Proving Ground represented the Allied effort to understand German equipment through systematic technical analysis. Mitchell had been trained as a mechanical engineer before the war and understood that captured equipment could provide insights into enemy capabilities and limitations. His mission was to evaluate German technology for potential adoption by Allied forces while identifying weaknesses that could be exploited tactically. The Panther tank that arrived at Aberdeen in July 1944 had been captured intact during the Normandy fighting, when its crew abandoned the vehicle after a transmission failure. The tank showed minimal combat damage, suggesting that mechanical problems rather than enemy action had caused its loss. Initial examination revealed a vehicle that represented advanced engineering concepts compromised by production shortcuts and design flaws. The massive tank dominated the testing facility as Mitchell's engineers began their systematic evaluation. At 45 tons, the Panther was significantly heavier than any Allied tank in service, yet its sloped frontal armor and long-barreled 75mm gun demonstrated sophisticated design concepts. The vehicle's external appearance suggested German engineering at its finest, but appearances were deceiving. Mitchell's team began their analysis by operating the Panther under controlled conditions to evaluate its performance characteristics. They discovered that the tank performed well during normal operation, but experienced increasing vibration and noise when subjected to the kind of stress that would be routine during combat operations. The transmission appeared to be operating at the limits of its design capabilities, even under ideal testing conditions. The first tests involved driving the Panther through obstacle courses designed to simulate battlefield conditions. Under normal acceleration and steering, the vehicle performed admirably, demonstrating the kind of power and agility that made it feared by Allied tank crews. But when subjected to rapid direction changes and emergency stops, disturbing symptoms began appearing that suggested fundamental problems with the powertrain system. Engineers monitored transmission temperatures during testing and discovered that the final drive assemblies reached dangerous heat levels during sustained operation. The inadequate cooling systems could not dissipate the thermal energy generated by the stressed components, creating conditions that accelerated wear and increased the likelihood of catastrophic failure. German engineers had designed the transmission for ideal operating conditions that rarely existed in combat. Detailed examination of the transmission components revealed the fundamental design flaws that were causing field failures. The final drive assemblies used gear arrangements that were adequate for normal operation, but lacked the safety margins required for military equipment. Material analysis showed that components were manufactured from steel alloys that met peacetime standards, but were inadequate for the stress concentrations generated during combat maneuvering. The most shocking discovery came when Mitchell's team calculated the expected service life of critical transmission components under combat conditions. Their analysis suggested that Panther final drives would fail after approximately 150 hours of operation, far less than the minimum requirements for military equipment. The failure rate meant that most Panthers would experience transmission problems within weeks of entering combat. Metallurgical analysis revealed that the steel used in critical transmission components had been selected for manufacturing efficiency rather than durability. German engineers had specified alloys that could be machined quickly and required minimal heat treatment, but these materials lacked the strength characteristics needed for shock loads. The compromises that enabled rapid production created weaknesses that guaranteed premature failure under stress. The gear tooth profiles showed evidence of inadequate engineering analysis that failed to account for the dynamic loads generated during combat maneuvering. German designers had used standard automotive practices that were appropriate for civilian vehicles but insufficient for military equipment. The result was gear systems that operated smoothly under normal conditions but failed catastrophically when subjected to shock loads. Most revealing was the absence of redundancy in critical transmission components. Civilian automotive practice accepted occasional failures because replacement parts and repair facilities were readily available. Military equipment required backup systems and fail-safe designs that allowed continued operation even when primary components failed. The Panther's transmission lacked these safety features, making any component failure potentially fatal for the crew. Engineering analysis revealed that the transmission failures were not random mechanical problems, but predictable consequences of fundamental design compromises. The lightweight construction that made rapid production possible also eliminated the redundancy and safety margins that ensured reliable operation under stress. Components were designed to minimum specifications without accounting for the shock loads and thermal stress generated during combat operations. Mitchell's report to Allied intelligence provided detailed technical analysis of the Panther's transmission problems and recommendations for tactical exploitation of these weaknesses. He suggested that Allied forces could expect significant numbers of German tanks to be lost to mechanical failures rather than combat action. More importantly, his analysis indicated that forcing Panthers to maneuver aggressively would accelerate transmission failures and reduce German combat effectiveness. The intelligence implications extended beyond immediate tactical considerations to strategic assessments of German industrial capabilities. The transmission problems suggested that German engineering was being compromised by production pressures and resource limitations that were affecting the quality of military equipment. Allied planners began incorporating transmission failure rates into assessments of German armored strength and operational capabilities. Field reports from Normandy and subsequent campaigns confirmed Mitchell's predictions about Panther reliability problems. Allied tank crews reported increasing numbers of encounters with immobilized German tanks that showed no signs of combat damage. Intelligence analysis of captured equipment revealed consistent patterns of transmission failures that supported the Aberdeen findings about fundamental design flaws. The Panther's transmission problems also provided insights into broader issues affecting German war production. The compromises that made rapid tank production possible were symptomatic of resource shortages and time pressures that were degrading the quality of German military equipment across multiple categories. Similar problems were being discovered in German aircraft engines, naval systems, and infantry weapons. German attempts to address the transmission problems through design modifications and improved manufacturing processes came too late to affect the war's outcome. Engineering teams developed improved final drive components that addressed some reliability issues, but production facilities lacked the capacity to implement major design changes while maintaining vehicle output. The fundamental compromises that created the transmission problems could not be resolved without completely redesigning the powertrain system. Post-war interrogation of German engineers revealed the extent of the pressure they faced during Panther development and the compromises they were forced to accept. Heinrich Kniepkamp and his colleagues understood that their transmission design was inadequate for combat operations, but production deadlines and resource limitations made proper engineering solutions impossible. They had been ordered to prioritize immediate deployment over long-term reliability. The human cost of these engineering compromises was documented through analysis of German tank crew casualties and vehicle loss rates. Panthers were lost to mechanical failures at rates significantly higher than other German tanks, and crew casualties were elevated because transmission failures often occurred during combat, when evacuation was impossible. The design flaws that enabled rapid production became death sentences for the men who operated the vehicles. Modern military engineering has incorporated lessons learned from the Panther's transmission problems into current tank development programs. Contemporary specifications include extensive testing requirements that ensure mechanical systems can withstand combat stress without failure. Reliability standards now mandate safety margins that prevent the kind of catastrophic failures that plagued German tank crews during World War II. The technological evolution of tank transmissions reflects understanding gained from analyzing German design compromises and their consequences. Modern powertrains use robust components and redundant systems that maintain operation even when individual elements fail. Advanced materials and manufacturing techniques provide the strength and reliability that German engineers attempted to achieve through design optimization. The strategic implications of the Panther's problems extend beyond military history to influence contemporary discussions about defense procurement and equipment development. The German experience demonstrates how production pressures and resource limitations can compromise engineering integrity with catastrophic consequences for the personnel who depend on that equipment. Modern acquisition programs incorporate safeguards designed to prevent similar compromises. Industrial considerations also influenced post-war tank development as Allied nations applied lessons learned from German engineering failures. American and British tank programs emphasized reliability and maintainability over performance optimization, recognizing that the most advanced technology was worthless if it failed under combat conditions. Soviet tank development incorporated similar principles while maintaining their emphasis on mass production. The legacy of Allied technical intelligence extends throughout the Cold War period as captured German technology influenced tank development on both sides of the Iron Curtain. Soviet tank designers studied German transmission systems while developing their own heavy tank programs. American engineers incorporated German innovations while avoiding the design compromises that caused reliability problems. John Mitchell continued his engineering career after the war, eventually becoming a senior designer for American tank programs that incorporated lessons learned from analyzing captured German equipment. His work on transmission systems reflected understanding gained from studying the Panther's design flaws and the consequences of engineering compromises made under wartime pressure. The Aberdeen Proving Ground analysis of captured German equipment became a model for technical intelligence programs that continued throughout the Cold War. The systematic approach developed during World War II provided frameworks for evaluating foreign military technology and identifying both capabilities and limitations that could influence tactical and strategic planning. Engineering education has incorporated the Panther transmission case study into curricula that teach the importance of reliability engineering and the consequences of design compromises. The German experience demonstrates how even brilliant engineering concepts can become catastrophic failures when fundamental principles are sacrificed for expedient solutions. The human dimension of engineering decisions remains central to contemporary discussions about military equipment development. The Panther's transmission problems serve as a reminder that technical compromises have real consequences for the people who depend on that equipment for their survival. Engineers working on current military programs understand that their decisions can determine whether personnel live or die in combat situations. Heinrich Kniepkamp survived the war and continued working as an automotive engineer, though he rarely discussed his role in tank transmission development. His post-war writings emphasize the importance of maintaining engineering integrity, even under extreme pressure, and the tragic consequences of compromising reliability for expedient solutions. He viewed the Panther's transmission problems as a personal failure that had cost lives. The technical documentation preserved at Aberdeen Proving Ground continues to provide insights into German engineering capabilities and the pressures that influenced their design decisions. Mitchell's analysis remains a definitive study of how production demands can compromise engineering integrity, with catastrophic consequences for equipment reliability and crew survival. That's how Allied engineers discovered the design error that was killing German tank crews through systematic analysis of captured equipment that revealed fundamental engineering compromises made under wartime pressure. The investigation happened through careful technical evaluation that demonstrated how production shortcuts had created mechanical systems that prioritized manufacturing speed over crew survival, turning Germany's most advanced tank into a death trap for its operators.